Electrophilic aromatic substitution. Okay, so in organic chemistry class, you learned that a benzene ring is a very stable compound. Usually they tell you it's unusually stable, quote, unusually stable, and you don't think that anything can touch it. Well, in organic chemistry, rules can always be broken. First thing you look at on this ring is these groups that are attached to it. These groups are what we call activators. Some groups are activators, some groups are deactivators. And I'm going to explain to you why these groups that I have on this ring are activators, meaning they make the ring more nucleophilic. Activators are groups that donate electrons into the ring. And sp3 hybridized oxygens will donate electrons into an aromatic ring. Why? Well, when you look at resonance, I'm just going to put one OH group in here for right now. Now, this oxygen has lone pairs on it, and these lone pairs can donate into the pi system of the ring by resonance. And I'm going to show you how. These electrons can come down, and the pi bond that is on this carbon can go on to the adjacent carbon and form an anion, giving you this. And this is just a resonance form of phenol. I drew a phenol right here, and this is just another resonance form. So you're going to get this. Okay. This is a resonance form. So you see how by these electrons coming down by resonance, I donated, this is an anion, a carbon ion. I donated electrons into the ring, making it more nucleophilic. Now, you go back to the products, I have two of those groups on here. So that's pretty good activation. So I'm going to, it's supposed to be BR2. Look at me making mistakes. All right. So basically, iron bromide is going to make an electrophilic bromine by, well, this is a little bit of inorganic chemistry for you, but okay, you got FeBr3. This is coordination chemistry. This iron has an empty orbital. You have bromine molecule. This bromine has lone pairs. This bromine can dump lone pairs into this empty orbital of the iron and bring this bond with it, leaving this bromine over here electron deficient. So, thus, this all makes FeBr4 plus, and then, I'm sorry, FeBr minus Br plus. Let me draw that. I'm sorry if this video is a little shaky, but this is for my cell phone. So, FeBr plus FeBr. It makes this ion, and it's going to give you this electrophilic bromine to add to that ring. You're adding electrophiles to the ring in this reaction. So now that you know we have Br plus, we can do our electrophilic aromatic substitution. Okay. So the first thing that's going to happen is, well, I'll explain ortho and para directors, but right now I'm just going to tell you that since these are activators, it's going to add ortho or para to these groups. Since these groups, the ortho and para positions of both of these groups are here, here, and here. But I'm going to only brominate these two positions. Well, actually, I'm going to brominate this position. I'm just going to show you how it works. I'm not going to brominate all the possible positions. So you have a bromine, right? A nice electrophilic bromine. And remember how double bonds are nucleophilic, right? This electrons from this double bond are going to come attack that electrophilic bromine, thus forming and you're going to have that, and you're going to have a plus charge on that carbon. Now, you still have a hydrogen on this, you still have a hydrogen on this ring. Now, you could do an addition to this ring, but this ring would rather go elimination to get back to its aromatic ring. It wants to be aromatic, so you will not do an addition. You will do an elimination to get back to the aromatic ring. That's what it wants to be in. So these electrons will come back and form the double bond, and this H plus will leave, thus giving you that. Now, I guess I have enough time to explain ortho and para. All right. Ortho, para, and meta. Let me redraw the starting reagents. Okay. So you have a phenol. Electron donating group into the ring. It donates electrons into the ring. Now, if it's an electron donating group, and when you do electrophilic substitution, the intermediate involves a carbocation inside the ring. So you want a carbocation to be able to form where it can land on an electron donating group. And the only way it can do that is if it adds ortho or para to the ring. So if you do a bromination, Br plus, these electrons go up there. You're going to form a cation on a carbon that has the electron donating group on it. You want an electron donating group onto a positive charge because it's electron deficient. So what better to be on an electron deficient carbon than an electron donating group? Perfect match. Perfect match in harmony. So that's why adding ortho to an electron donating group is good. Now, adding para. So you have Br plus these. Now, let's go from there. Okay, so that, oh, damn it, look at me making mistakes again. Okay, so you're gonna have positive charge right there. It's not an electron donating group, right? Well, if you do a little resonance, you could bring this double bond that's right here over here, and now that will bring I'm sorry, bring it, I did it wrong. Bring it over here to this bond, and that will move the positive charge from here to here. So now you can see, even when you add to the para position, the positive charge can go on this carbon with the electron donating group by resonance. So it's not directly on that group, but it can go there by resonance. So when you have an electron donating group, the electrophile will add to the ring either in the pair position, which is directly across, or the ortho position, which is directly next to the electron donating group.